So far in Chapter 7, we have taken a rather simple view of covalent bonding, based primarily on the use of Lewis structures for electron bookkeeping. Lewis structures, however, tell us nothing about why covalent bonds are formed, or how electrons manage to be shared between atoms. Vesper theory is useful for predicting molecular geometry, but it doesn't tell us why electrons group themselves into the domains that they do. These models are simple and helpful, but we want to expand on them a little bit and understand some advanced topics within covalent bonding. Modern theories of bonding are based on the fact that electrons behave like standing waves when confined to atoms. Atomic orbitals are mathematical representations of these waves in atoms. In molecules, we can explain how atoms form a covalent bond if we can understand how the orbitals of the bonded atoms interact with each other. There are two major bonding theories that have evolved. The first one is called valence bond theory, and the second one is called molecular orbital theory. Molecular orbital theory is a little bit advanced, and we probably will not focus much on it within this course. Therefore, in Chapter 8, we will spend our time understanding valence bond theory in depth. The bonding theory that we're going to spend most of our time on in this chapter is valence bond theory, sometimes abbreviated VB for short. According to valence bond theory, a bond between two atoms is formed when a pair of electrons, with their spins paired up, is shared by two overlapping atomic orbitals, or later we'll also see hybrid orbitals, one from each of the atoms, and they're joined by a bond. So the important parts of valence bond theory that we're going to focus in on is that we're going to need to have two electrons that are brought together, and when they are, those electron spins will become paired. And if you recall, we previously learned that we had spin up and spin down, which is when we had those together, we said that our spins were paired in an orbital. And we have to be able to have at least one half-filled atomic orbital overlap with another half-filled atomic orbital in order, when they come together, for their spins to be paired and there to be two electrons in the bond. The electrons will live in the bonds between these atomic, or later we'll see, hybrid orbitals. Let's imagine what happens as two separate hydrogen atoms come together to form a covalent bond in the molecule H2. H2 is a simple molecule where there's just one single bond between each hydrogen atom, which represents two electrons being shared. Each hydrogen has one electron in its half-filled 1s orbital. If we imagine the two hydrogen atoms starting far apart, so far apart that they essentially have no interaction, let's imagine what happens as they move closer and closer together. As they get closer together, eventually the energy is going to drop. The energy falls to a minimum point of the molecule when they reach the optimum distance. That optimum distance leads to a lowering of the potential energy when that H2 molecule is formed. We can think of this energy as the bond energy, or the energy that would be required to break that covalent bond when they reach that distance apart. The bond length, or the internuclear distance, when we are at that potential energy minimum, represents the length between our two hydrogen atoms, or essentially the length of our covalent bond. If our two hydrogen atoms were to come any closer past that minimum potential energy, the energy would shoot back up, because now we do not have that balancing act of attractions and repulsions in our molecule. The lowest energy represents the most stable distance for those two hydrogen atoms to be. Here we have a balancing act between the repulsions between our two negative electrons and the two positive nuclei, along with the attractions of a nuclei pulling in the electrons within the covalent bond as well. Next, we are going to practice some examples of using valence bond theory to fully describe bonding in some various molecules. When we say fully describe, we want to write it out in words and often draw a picture of the bond we're trying to describe. So we're going to start simple with H2, And there are some steps that we can take in order to help us in our description of what's going on in that bond when it's formed. So I recommend first starting off with drawing a Lewis structure of the molecule that you're trying to describe the bonding for. So our valence electrons in H2, we're going to have one for each hydrogen times 2 because there's 2 hydrogens. So 2 valence electrons to place. Our Lewis structure will be hydrogen with a bond to the second hydrogen. And that covalent bond represents those 2 electrons being shared. That's going to be the bond that we are going to be describing using valence bond theory. So we have one single bond to describe in this example. Let's think about, after we draw the Lewis structure, what is our electron configuration for our atoms that are involved in the bond? Since both of our atoms are hydrogen, we just have one electron configuration to write. Hydrogen's configuration is 1s1. After we write the electron configuration, let's also draw the orbital diagram. The orbital diagram gives us a little bit more information because it shows us specifically what orbitals our electrons live in. So in hydrogen, we have our 1s orbital, and we have one electron, and we'll draw it as spin up, occupying that 1s orbital. Our other hydrogen atom has the exact same electron configuration, 1s1, and it also has a half-filled 1s orbital that we can see with our orbital diagram. Valence bond theory says that it's important to have half-filled orbitals overlapping so that when the electrons come together, their spins can become paired. So here we have one half-filled orbital. So we have a half-filled 1s orbital to be specific. And here we have another half-filled 1s orbital on our other hydrogen atom. And we know the shape of our orbitals. S orbitals are spherical. So what our picture is going to look like is we're going to have a 1s orbital on one of our hydrogen atoms, and it's going to come closer and closer and closer together with our other hydrogen atom, which is also bonding with a 1s orbital until they overlap. So right here we have both of them overlapping, both 1s orbitals, and each brought to the dance one electron. And we need 2 electrons together to make a bond. So when those electrons come together, they're going to come together in that region of overlap. Their spins are going to be paired. So therefore we show the spins being paired with an up arrow and a down arrow. And that region of overlap where those spins are paired represents the covalent bond that we formed. Now, how orbitals overlap will determine what type of bond specifically is formed. So this is our first example. If we imagine that there is an imaginary x-axis running through our molecule, this will help us differentiate between the different types of bonds that we can see. This is called the internuclear axis. And you can think about it just like I said, an imaginary x-axis running through your molecules where they overlap. And in this example for H2, we see that our bond was formed from the direct overlap of those 2 half-filled 1s orbitals right along the internuclear axis. So in this case, we had direct overlap. Or we can see that there was only one location where those 2 spheres overlapped. So sometimes direct overlap is referred to as overlapping in only one spot right along the internuclear axis. So it's important that the electron density now, where the bond is going to be formed, is happening right along our imaginary x-axis. And the type of bond that's formed when we have this direct overlap is called a sigma bond. So we can write out the word sigma, or you might see the Greek letter sigma used. Sigma bonds are formed when half-filled orbitals interact directly along that internuclear axis. That's when we refer to that orbital overlap as being a sigma bond. So we can see that a single covalent bond is made up of one sigma bond only. So if we were going to use valence bond theory to put all of this information into words and to fully describe our bonding in H2, we could say something along the lines of the single covalent bond in H2 is the result of a half-filled 1s orbital on each hydrogen atom overlapping directly along the internuclear axis to form a single sigma bond. When we use valence bond theory to describe bonding, there's a few key points we want to hint on in order to describe the bonding completely. We talked about that we had a single covalent bond in H2 that we had to describe. We talked about that we had half-filled orbitals, which are important according to valence bond theory. We said specifically what orbitals were overlapping on each atom. We had a 1s orbital. We talked about how they were overlapping, in this case directly along the internuclear axis. And we said what type of bond we formed, in this case a sigma bond. Those are going to be the key points you want to hint on in your description of bonding when you use valence bond theory. There's no right or wrong way to put it into words, but you want to talk about those specific things. Use valence bond theory to fully describe the bonding in HF. First, let's draw our Lewis structure for HF so we know exactly what type of a bond we have to describe. Here we have fluorine having a complete octet. It has 3 lone pairs and it has 1 bonding pair. Hydrogen follows the duet rule, so it has 2 electrons from the covalent bond. In HF, we have 1 covalent bond to describe, which is a single bond between hydrogen and fluorine. And this single bond is different than the single bond we saw between hydrogen and hydrogen. But our Lewis structure alone doesn't explain why. So that's why we'll use valence bond theory to specifically think about what type of orbitals are overlapping and how they're overlapping. Start off by writing your electron configuration for both of your atoms involved in the bond. We saw hydrogen was 1s1. The electron configuration for fluorine, we can just write the shorthand configuration because we only care about the valence electrons. Helium, brackets, brackets, 2s2, 2p5. After we write our electron configurations, it's best to look at our orbital diagrams. So for hydrogen, we're going to have a 1s orbital, and we're going to have 1 electron in that 1s orbital, so that one's half filled and ready to form a bond. For fluorine, if we draw our orbital diagram, we'll have our 2s orbital, and that will be completely filled because there's 2 electrons already in there. And then we have 3 equal energy 2p orbitals, and there's 5 electrons we have to populate. So we're going to have 1, 2, 3, they all half fill, and then 4, 5. So valence bond theory says we have to have half-filled orbitals that can overlap. So where are our half-filled orbitals? We've got 1 half-filled orbital on our 1s for hydrogen. And notice we have 1 half-filled orbital for one of our 2p's on fluorine. The other 2s and 2p orbitals on fluorine that are filled would be representing those 3 lone pairs that we see on our fluorine atom. So when hydrogen and fluorine come together with their 1s orbital on hydrogen and their 2p orbital on fluorine, we're going to be forming a single bond between them, one single covalent bond. So what is that going to look like if we draw a picture? So hydrogen brings a half-filled 1s orbital to the dance, and fluorine is going to bring a half-filled 2p orbital. So s orbitals are spherical, and if you recall, p orbitals kind of have a dumbbell or a bow tie shape, and so we're going to represent that accurately. So we're going to draw our 2p orbital on fluorine. This region of overlap is going to represent our bond being formed, and one electron will have a spin up, the other electron will have its spin down. So our spins are paired within that region of overlap, therefore that is our covalent bond. Here is our region of overlap representing our bond. And once again, think about that imaginary internuclear axis, or that x-axis, running through our s orbital and our p orbital. The region of overlap is directly in one location right along that internuclear axis. So once again, we formed a sigma bond. So this is the second way that we can actually form a sigma bond, where we have a 1s orbital directly overlapping with a 2p orbital, or just in general an s orbital overlapping with a p orbital to form a sigma bond because of that direct overlap in one location. So if we were going to describe our bonding in HF and put it into words, what's happening here, we would say that the single covalent bond in HF is the result of one half-filled 1s orbital on hydrogen overlapping with one half-filled 2p orbital on fluorine with direct overlap along the internuclear axis. So let's check back in our terminology and kind of see if we hit all those main points that valence bond theory says is important. So we had our half-filled s orbital. So we talked about the orbital being half-filled, and we specified what orbital it was. We had a half-filled 2p orbital. Same thing, we talked about it being half-filled, and that we were using a 2p orbital on fluorine. We had direct overlap along the internuclear axis, but we also have to state what type of bond was formed. So after we say that we had direct overlap along the internuclear axis, we also have to add to form a sigma bond. So that's the last thing we have to include. What type of bond was formed? We had a sigma bond, which represents a single covalent bond in our molecule. Use valence bond theory to fully describe the bonding in F2. If we start by drawing our Lewis structure for fluorine, or F2, we would end up having a single bond between each fluorine atom, and there would be a complete octet around all of them to place all of the electrons. So this is going to be the last single bond that we describe or do an example of. Here we have another single bond, but it's not going to be the same as the first two single bonds. So a single covalent bond And we'll see what makes this one different. So now we have two fluorine atoms overlapping to form a single covalent bond. So we're going to have our electron configuration for fluorine that we need first. And our configuration can just be the shorthand notation. So helium brackets brackets, 2s2, 2p5. And that's going to be the same on each fluorine atom because they're identical. Next, if we draw out our orbital diagram, we have our 2s orbital that's filled. We have our 3 equal energy 2p orbitals with 5 electrons to draw in there. Same thing for our other fluorine atom. We're going to have our filled 2s that won't be involved in bonding, and our 5 electrons in our 2p subshell. Looking here, we can see we have one half-filled 2p orbital on one of our fluorine atoms, and we have another half-filled 2p orbital on our other fluorine atom. Those half-filled 2p orbitals are going to be what overlaps in order to form our single covalent bond between F2. And we said that F orbitals, or P orbitals, look like a dumbbell. And so we're going to have one P orbital lying directly along the internuclear axis, overlapping with another P orbital lying directly along the internuclear axis here. So here's our imaginary internuclear axis running through both of our sideways P orbitals. And how they're overlapping, they're still overlapping in a way that there's only one region where they're interacting. So the electrons will come together in that region of space, their spins will become paired, and this highlighted spot right here represents our single covalent bond. So this is the last way that we can actually form a sigma bond, which we saw that a sigma bond had that direct overlap. So the first way we made a sigma bond was SS overlap. The second way was SP overlap. And here we have p orbital overlap. We could imagine calling this p orbital on the left px and this one on the right px as well, because they're both lying along our internuclear axis, which is a lot like an x-axis. We know our other 2p orbitals on each fluorine atom are present, they're there, but they're filled up with electrons already, so they're not involved in the bonding. Those would be imaginative being py and pz. We'll talk more about those later. So if we're going to use valence bond theory in order to describe our covalent bond in fluorine, we could say something along the lines of the single covalent bond in F2 is the result of one half-filled 2p orbital on each fluorine atom overlapping directly along that internuclear axis in order to form a single sigma bond. So we hit on all of those key points. We talked about having half-filled orbitals. We said what orbitals specifically. We said what type of bond was formed. And so far, the only type of bond we've really talked about is a sigma bond. And those are kind of the major things that I'll be looking for in your descriptions using valence bond theory. Here's a little bit of a nicer picture showing you the 3 different types of sigma bonds that we saw. So a sigma bond was a covalent bond where the electron density was concentrated directly along the internuclear axis. So that was that direct overlap in one location. Sigma bonds could arise from the overlap of 2 s orbitals, and this would be our picture for 2 s orbitals in A. And here is our region where the overlapping occurs, where the electron spins are paired. Or B, the overlap of an s orbital and the end overlap of a p orbital. Here is where our sigma bond would be formed in B. And C, the end-to-end overlap of two p orbitals. And C, here is going to be where our electrons become paired, right in that region of overlap. And so that would represent the third type of sigma bond that we saw. So you can imagine why, even though they all are single covalent bonds, why they would have different bond energies and the energy required to break that bond, because they're different orbitals overlapping to actually form that single covalent bond. Use valence bond theory to fully describe the bonding in O2. So in this example, we're going to build upon what we already saw and take it to the next step. So if we draw a Lewis structure for oxygen, or the molecule O2, we would see that we would end up having a double bond between each oxygen atom. So now when we use valence bond theory, we're going to have to describe a double bond. Start by writing out our electron configuration. So on one of the oxygen atoms, our shorthand configuration is going to be helium 2s2 2p4. Our other oxygen atom is going to have the same electron configuration. Drawing out our orbital diagram. So we have our 1, 2s and our 3, 2p orbitals. Our 2s is completely full. We have 4 electrons to throw into our 2p orbital. So 1, 2, 3, and then 4. Our other oxygen atom is going to look identical. A completely filled 2s orbital and 4 electrons spread out amongst 3 2p orbitals. So now when we go to look for our half-filled orbitals that could possibly overlap, we can see that there are 2 half-filled orbitals on just one of our oxygen atoms. So here's our half-filled orbitals for this oxygen atom. And our other oxygen atom is going to also have 2 half-filled orbitals that could overlap. So that's going to make for the formation of 2 different bonds, or 2 regions where there's going to be electron density located. When these 2 half-filled orbitals come together on each oxygen atom, we'll be able to draw that and show the formation of our double bond. Let's start with what we just saw for F2, essentially, where we use 2 of our half-filled p orbitals, one on each oxygen atom, directly along the internuclear axis. So let's call this one 2px, and this one 2px, and our other one, let's refer to it as 2py. 2py. We can think about them as lying along the x, y, and z coordinates. So for our 2px, we're going to have 1 p orbital on one oxygen atom, and we're going to have another 2px orbital on the other oxygen atom. Here is our imaginary internuclear axis, or our x-axis, running through both of those 2px orbitals. So 2px here, 2px here. Our region of overlap, where one electron from each 2px orbital comes together, is directly along the internuclear axis right here. So here's our region of overlap. So when the 2px orbitals come together, this would represent a sigma bond. So the first type of bond that's formed is that single sigma bond from that direct overlap along the internuclear axis. And now let's think about our 2py orbitals. So let's imagine those are 90 degrees or perpendicular to our internuclear axis. So one of the 2py orbitals would be pointing straight up from our internuclear axis. And here's the other 2py orbital on the other oxygen atom. Now in our drawing, it doesn't look like they're interacting at all. It doesn't look like there's a region where there's overlap. So we have to imagine this. We have to imagine that the top lobe on both of the orbitals would have some region where those electron waves are interacting. and the bottom part of them as well. So here we have two side-by-side p orbitals. They're not overlapping directly, but they're overlapping perpendicular to the internuclear axis. So we can imagine that the electrons will become paired, and they could either be in the top lobe or the bottom lobe. So let's draw our overlap of those two electrons with their spins coming together. And so this region below represents part of the second bond, and this region above represents the other half of the second bond being formed. So that region above and below together, these two spots, is one bond. And this is called a pi bond. Pi bonds are different than sigma bonds because they are only formed from the sideways overlap of two p orbitals. So if we draw these two p orbitals closer together like this, we can see that here is one region of overlap and another region of overlap. There's two spots where they overlap above and below our internuclear axis. So they're not directly overlapping. We refer to them as being a sideways overlap because that overlap happens in two locations, above and below our axis, 90 degrees to that. So when we describe our bonding in O2, we have to fully describe our sigma bond that's formed and our pi bond that's formed. Any double bond is going to be one sigma plus one pi bond together. Let's put all of this into words using valence bond theory. The double bond in O2, that's what we're going to be describing, is the result of direct 2px overlap to form a sigma bond, and sideways two py overlap to form a pi bond. Each 2px and 2py orbital on oxygen is half filled. So we wanted to make sure to describe the sigma bond and how it was formed. That was formed from 2px overlap directly along the internuclear axis. So we used the words direct to describe that and said it formed a sigma bond, said what specific orbitals were overlapping. And then we also talked about the sideways overlap from those two py orbitals, and they overlapped in two locations to give us that pi bond. Each of those coming together were half-filled orbitals, which then allowed the electron spins to be paired up when that bond was formed. Here is a little bit of a nicer image showing that side-by-side p orbital overlap that overlaps in two locations. So here's location 1, here's location 2. The electrons would be shown as being paired up in either one of the two spots. And that has a node running through the middle because p orbitals have a node in the middle, and that node is directly along that internuclear axis there. So anytime we form a pi bond, it's going to be from side-by-side overlap of two p orbitals. And it's going to run perpendicular or 90 degrees to the internuclear axis. All right, here is our last example using valence bond theory to describe the bonding in simple molecules. So for N2, if we draw the Lewis structure, we would have nitrogen triple bonded to another nitrogen with a lone pair of electrons on each nitrogen. So we're going to describe what's happening when we form a triple bond. Start with our electron configuration for nitrogen. We're going to have helium in brackets, 2s2, and then 2p3 because there's a total of 5 valence electrons in nitrogen. We can see those in the n equals 2 level. And then our other nitrogen atom is going to have the exact same electron configuration. So helium 2s2, 2p3. Our orbital diagram, draw our 2s and our 2p orbitals. 2s is filled. Now we have 3 electrons to place in our 2p orbitals. So we're going to have 1, 2, 3. Same thing for our other nitrogen atom. 2s, 3 equal energy 2p orbitals, and there'll be 3 single electrons, 1 in each of the 2p orbitals. Now, looking at our 2p orbitals, we have 3 half-filled 2p orbitals just on one nitrogen atom. And then we have 3 other half-filled 2p orbitals on the other nitrogen atom. So let's imagine that our orbitals represent 2px, 2py, and 2pz. Same thing for the other one, 2px, 2py, 2pz. Our p orbitals are all going to be dumbbell-shaped, and they're going to lie along the x-axis, y-axis, and z-axis, which is going to be a little bit tricky to try and draw. So if we start with our 2px, because that's the easiest one, we're going to have one 2px orbital for one nitrogen atom, and that's going to overlap with another 2px orbital on the other nitrogen atom. And this is one we've seen quite a few times now. We have our 2 electrons coming together. The spins are paired. Our region of overlap right here is representing our first bond, which is our single sigma bond, first and foremost from that direct overlap along the internuclear axis. So let's draw in our internuclear axis. Next, we can show our 2py orbitals overlapping 90 degrees to our internuclear axis. So let's use a different color here. Here's one 2py orbital on one nitrogen. Here's another 2py orbital on another nitrogen. Those orbitals overlap above and below the internuclear axis. So here's one region of overlap. Here's another region of overlap. And that region of overlap above and below, or sideways, where the electron spins come together and are paired, that's referred to as a pi bond. And this is where we stopped with oxygen. We had one sigma bond and one pi bond, which represented a double bond. But now we have another half-filled 2pz orbital that we have to consider. And those would really be coming straight out at us from our board right here and going right behind us. So I'm going to have to draw them on an angle in order for us to see them, but really they would be coming out straight at us. So if we draw in our last p orbital, we're going to have one going straight out, one going behind. They're also 90 degrees to the internuclear axis. And where these overlap are in 2 locations, one right here and one right here. The electrons will be located in one of the regions, so 2 electrons coming together, and their spins are paired. And so here's overlap showing in yellow, and here is the other side, the other lobes overlapping in yellow. And those would be our 2pz orbitals. And so whenever we have a triple bond, we have a combination of 1 sigma bond plus 2 pi bonds. The 2 pi bonds are the result of the py orbitals overlapping above and below the internuclear axis and the 2 pz orbitals overlapping 90 degrees to that internuclear axis, just coming straight out and straight behind from the plane of our board here. And so if we were going to describe our bonding using valence bond theory in nitrogen, we would say something along the lines of the triple bond in N2 is the result of 2 px orbitals overlapping directly along the internuclear axis, or 2 half-filled 2 px orbitals forming a single sigma bond, and 2 half-filled 2 py and 2 pz orbitals overlapping sideways perpendicular to the internuclear axis to form 2 pi bonds. A triple bond is made up of a sigma and 2 pi bonds. So all of those things we want to include in our description to fully describe the bonding according to valence bond theory. So here is a summary on the different types of bonds that we saw. All single covalent bonds are made up of one sigma bond. There's no pi bonds anytime you just draw a Lewis structure and you have one single bond. That would just simply be a sigma. When we draw a double bond, which is representing 4 electrons being shared, whereas a single bond was showing 2 electrons being shared, double bonds are made up of 1 sigma bond and 1 pi bond. A double bond is not equal to a pi bond. That's a simple mistake that I see a lot of people make. There's 2 different regions where electron density is located, directly along the internuclear axis, which is our sigma bond, and above and below the internuclear axis, which is our pi bond. A triple bond has 6 electrons held between there, and there is electron density held directly along the internuclear axis. That was our single sigma bond that we saw, so there's 1 sigma bond first, and then we formed 2 pi bonds following that because we had 2 regions where there was sideways overlap of p orbitals. So any triple bond will be 1 sigma plus 2 pi bonds. Let's practice identifying the number of sigma and pi bonds within a molecule. Butadiene is an organic compound made up of carbon and hydrogen, and we want to figure out the total number of sigma and pi bonds. So we learned that every single bond is composed of just a sigma, so let's write those out. Every carbon-hydrogen bond is a single bond, so those are all going to be 1 sigma. And then we have a carbon-carbon bond right here, which is a single bond, so that's going to be 1 sigma bond. The other 2 represent carbon-carbon double bonds. So here's 1 carbon-carbon double bond, and here's the other. And we said that a double bond is going to be a sigma plus 1 pi bond. So we have another sigma and another pi bond for the other double bond. So our total number of pi bonds in this molecule is going to be equal to 2. In our sigma bonds, we're going to have to add them up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to have 9 sigma bonds.